We actually used to have physical events before COVID. This is the first physical event post-COVID. So welcome to this. We're talking about AI, ML and verification. I don't think we had a single event before COVID on this. So this is the change in verification that's happened since then. You can see our sponsors are there. Thank you to the University of Bristol for hosting TESOL. It's their last DV Club TESOL. In the future, I'll be running them as a final system. And TechWorks are a partner, and also Microelectronics UK, and they'll be talking about their event later. Okay, so we've got 345 attending person, 66, although we do seem to be down a bit in the room. It's a lot of no shows at the moment, but there are a lot of people remote, 270 remote, and we've got 134 companies in 40 countries, so truly international, not just Bristol. So yeah, we're going to try and fix it. So we've got a full set of speakers, 6 in all. We're breaking up. I won't go through them because we're a bit short time, we're a bit late. At 7 o'clock we'll wrap up, and there is pizza arriving at 1700. At 5 o'clock we'll wrap up, and there'll be some pizza arriving outside. So again, thank you, and we'll go straight into our first speaker. So our first speaker is Chris Bennett from the University of Bristol, where he's a senior research associate. The topic of his talk is a survey of research on machine learning for test-based verification. He's part of the SCHEME project, a consortium of UK industry and academia developing the next generation of microprocessors for use in aerospace and other harsh environments. And he's based in Bristol.
Okay. We are not able to hear the speaker.
Okay, you can hear me, Disha?
Yeah, now I can hear you. You can go ahead, please.
Lovely. All right. Yeah. We'll cope as best we can. It's going to be very strange for me as a speaker hearing my voice ring back with a slight delay, but it'll be fine. Okay. Good afternoon, everybody. Thank you, Mike. So today I'm going to talk to you about a piece of work we've been undertaking at the University of Bristol, which is a survey into the use of machine learning for test-based verification. I'm conscious we might have quite a diverse audience today, so just by way of a little bit of background. When we're talking about test-based functional verification, it's a process to ensure a design carries out its functions according to its specification. I use the word here is design is important. We're working with a functional representation of the device, not the physical device itself. You'll see me refer to the term coverage points. If you're not from a verification background, you can think of these as analogous to states of the device that relates to functionality that we wish to verify. In a typical test-based workflow, we generate stimuli. Looking at the diagram at the bottom, these are passed to a reference model of the design as well as the design itself that is simulated. We use a reference model to ensure, to generate the correct answer or the expected answer for the input presented to the design. The design is monitored, all the information gets passed to analysis and logging stage, and it's here that enables us to answer questions such as, was the result the design gave us expected, and which coverage points or states, if you prefer, the design hit during execution. Now, often the relationship between the internal states of the design that we're interested in verifying and the test stimuli provided to it is not obvious, and therefore the challenge is how do we choose all the inputs to hit the specified coverage points using the minimum amount of resources, and that's where researchers have looked to use machine learning. That's basically the background for our review. Now, it's worth saying we're looking at functional verification using machine learning for dynamic-based test methods. Now, functional verification is only one of the processes you undertake as part of a typical design process for a microelectronic device, and functional verification is only one of the methodologies you can adopt. I say this because as part of the review, we found machine learning research that covers everything on this slide, and many other areas that we didn't have space to fit on. So what I'm covering today is only one part of a much wider research effort, and hopefully some of the presentations this afternoon will cover some of that. I think it's fair to say there is a lot of interest in machine learning at the moment. The research is increasing, but not all of these techniques are being adopted in the real world. And our interest is, because it's an applied research, one of the questions I had starting this was actually what actions are needed to make better use of our existing techniques, and also what lessons can we learn for future research. Okay. Very quickly, so about how we source the data for this review. So we sampled the existing research literature, undertook a filtering process, and then to produce a set of research that we reviewed in detail. The results of that went into reports that you can currently read on arXiv. As part of that filtering process, it's based on an approach that was used in the 2023 paper, which looks at machine learning for software testing. You'll hear me speak a lot about classifications and groupings. We've made all these available in a data set that's open source that anybody can download. It took us about 6 months to do this identifying work, filtering, classifying. So anybody who starts from a data set should save a lot of time. Okay. So at the beginning of this work, I was really interested in how has machine learning typically been used in this area historically. So on the left, you'll see a count of the number of new techniques proposed by year. The right is a cumulative sum. Now, as I said, machine learning is generally increasing, and we see that reflected in the number of publications. But it's also interesting to note that the use of machine learning in hardware testing has been in research for about 25 years. So if we cut through the current hype surrounding machine learning, it's not new in this area. We include evolutionary algorithms in our sample. These have historically always been popular in this area, although more recently we see interest turning to other areas, including supervised learning and reinforcement learning. It's worth saying that many of the techniques we see in research here have been developed in other areas. So the trends we're seeing here are likely a reflection of the tools and algorithms that are being developed as part of the wider machine learning community. It's also interesting to compare research materials being published for software testing versus hardware testing. So up until about 2016, there'd been more research material published for machine learning in hardware testing. From 2016 onwards, we see this huge explosion in the amount of material for software testing, and we don't see that for hardware. Now, they treat with a huge amount of skepticism. However, it may be indicative that the amount of research in machine learning falling behind other areas relatively. That kind of brings us to first our reasons why we think there's been lots of research, but perhaps a low amount of adoption. It's fundamentally a hard problem to solve. That's why we're still looking at it after 25 years. Reasons for this? Well, often we're asking the machine learning to infer test inputs to a device to hit a coverage point that it hasn't seen during training. Often the similarity between two test inputs is not reflected in the similarity in the coverage space or between two coverage points. Different abstraction levels are a challenge. And also these techniques are intended to be used in a development environment where your design is changing regularly. Every time you change the design, you potentially change the ground truth relationship between the inputs and the coverage points or states that you're trying to hit. So it's a hard problem to solve. Okay, my next question after historical techniques was actually to look at what kind of algorithms and what have people used to solve this problem. And that's what's reflected on this slide. I'll kind of go through a few of these in detail. So supervised techniques are where we have labeled data. So for each input, we know the output. These are the most popular. About 50% of all the research use supervised techniques. Possible reasons: typical verification environment, you have a lot of labeled data potentially. Also, the tools and algorithms and workflows are fairly mature in the supervised techniques. Unsupervised techniques, that's where we're looking for relationships
or patterns in data.
Patterns in data.
Potentially explained by the abundance of labeled data.
Explained by the abundance of labeled data. Maybe research wants to use that more.
Reinforcement learning, we're looking
I'm sorry, Chris, to interrupt.
Feedback.
There is a echo going. There's two
So we're
voices
learning-
coming.
We're learning through feedback and trial and error. Receiving rewards or penalties from the environment.
These have been shown to be very effective for sequence generation in other areas. That might explain why research is looking at it for test generation. Evolutionary techniques are a little bit different. They're an optimization technique where you're using simulations of natural selection and evolution. They've been historically very popular in this area. One of the reasons may be that because they work with sets of solutions rather than a single solution, often testing you want more than one test, you want to generate many tests. And there are ways of using evolutionary algorithms to do that. Wait for the next presentation, you'll see a bit more about that. In terms of training methodologies, it's perhaps unsurprising that learning online is popular. Every time we run a simulation, we generate new information that we can use to improve our model. The problem with online learning is that your initial model tends to be quite poor and it improves over time. One way around that is to use any historical data that you have to bootstrap it, to create a good model to start with, and then you improve that with each simulation iteration. Surprising in some way, there aren't more hybrid techniques here seen in research. But the takeaway from all of this slide is there's lots and lots of different ways that researchers approached to solving this problem. And that brings us to our second reason. Why do we struggle for adoption? There's just so many options available to you if you want to apply this in your verification process. One way around this is to classify the research to make it easier to navigate. And that's what we do as part of the review, and other authors have done as well. To understand any classification, we need to understand how machine learning research modifies our typical verification environment. So on the slide here, you can see a very, very simplified version of a test bench that's used for electronic design verification. Now, often we generate tests randomly. So we use a pseudo-random test generator that enables an engineer to generate many tests from a single parameterization. That engineer is usually part of a feedback loop. So gaining information from the previous test being run, they change that parameterization to steer the design towards different functionalities of interest over time that we want to verify. All machine learning research in this area ultimately aims to improve efficiency. So that's either to reduce the amount of time the engineer is devoting to this or reduce the number of simulation cycles. So typically what machine learning does is we replace the human in the loop with a machine learning controller. This now takes feedback from previous simulations, historical data from a data repository, and proposes the next test to be run on our design. Two important points to note. Because, as I said, we're taking techniques from other areas, quite often an interface is used between the machine learning controller, written in a high-level language like Python, and then the verification environment, which is written in a domain-specific language such as System Verilog. The second point we also need to ask is our engineer now free to go and do other things? The answer quite often is no. What we've done is we've shifted the workload. The engineer is now responsible for maintaining and configuring a machine learning controller. That's one of the areas where we see more research needed, is into techniques that work out of the box and are easy to set up, deploy, and maintain. With this classification, using a machine learning controller model, we can then classify research. In the review itself, we look at different classifications, but this is a fairly simple one, and it's very effective. So we can classify controllers based on test generation, direction, or selection. In a generation scenario, the machine learning takes feedback, usually in the form of coverage information, and then suggests the next test in the form of a bit pattern or machine instruction, as well as a sequence length, directly. In test direction, that's similar to our existing verification environment. The machine learning is trained to direct something else to generate the tests. It's usually a constrained random test generator. There are certain advantages to test direction over generation. It's potentially an easier learning problem. We can embed a lot of the knowledge about what makes a legal and interesting test into the test generator. However, these test generators have very large parameter spaces. There's also now a probabilistic relationship between the test that's generated and the output of the machine learning model, and that can actually make learning more challenging. In test selection, the machine learning chooses from a set of pre-generated tests. We see three types in research. The first is optimization, where machine learning is choosing a subset of tests, usually offline. If you work in this area, that's similar to a regression set optimization problem. In test filtering, we're deciding to simulate a test on a case-by-case basis. That's usually done online in the main loop while the simulations are taking place. And a prioritization model where we're deciding what order to run our tests in on the basis that certain tests are more valuable, they hit more coverage points, we want to run those first. And let's move on to that. Okay, so with this classification, we can then make some very broad observations. So test generation tends to be the most powerful use of machine learning. It has direct control over the test content. It also requires the most amount of learning. Most amount of domain knowledge needs to be embedded in it, and we have to integrate it into our existing test loop. Something like test selection is simpler. It can be powerful, but it depends on the tests that are generated and presented to it. We've worked on selection techniques here at Bristol and Trustworthy Systems Lab, including novelty detection, which is a form of filtering technique. They're very effective. They can work out of the box as well. It's worth saying, if we look at other domains, there's usually a leading technology. So if you look at image classification, perhaps convolutional neural networks, if you're looking at, I don't know, transformers for large language models, text generation, translation, we don't see that here. There is no single one leading technology in this area. And actually, if you see the sort of split of the research, it's about an even split between direction, generation, and selection approaches to this problem. So if you think about somebody wanting to select a technique to use in their verification process, lots of options, quite hard to decide which one you should use. The question I had was really, all things being equal, which technique is better for a particular context? That led us to look at the way research has evaluated these techniques, in particular the baselines that they compared their techniques to, and the metrics they use to measure any improvement. So looking at baselines first, most research compared their new machine learning techniques to randomly generating instructions and feeding those into the design. Now, I will leave it to the audience to decide whether you think random is a good baseline. It's often used because it's the lowest common denominator. It's something that everyone can easily set up and apply. Next most common baselines, existing constrained random generation processes, and also prior art in machine learning tell us something about the incremental improvement of a technique. In terms of metrics, application performance is the most popular. That perhaps is unsurprising given it's an area of applied research. Counting the number of inputs supplied to the device, as well as how long it takes to execute your verification process, and both speak to efficiency. So that's not surprising they're popular. It is a little surprising we don't see learning performance metrics used more in the research. We might explain this by saying that because it's applied research, if a technique improves efficiency, we may not care how accurate it is or how well it generalizes. If you're coming from an area like medical, ask a question as to why that might be. But in this particular area, we maybe don't care. And what we do care an awful lot about is how much overhead does our machine learning add to our existing verification process. And actually, we see this tends to be underreported in the research to date. We also looked at how the designs that research used to test their techniques on. Now, on this kind of complicated chart, you can see that a block size indicates the number of examples of a particular design being used in the research. And the first thing that really struck me when I saw this chart was actually just variety. So we can see machine learning used to help verify processors. It's block level on a processor, accelerator designs, communication designs. And that tells us something about the variety of scenarios that machine learning can be applied to. That variety also represents a problem from somebody wanting to select a technique to use. Assessing the techniques on different designs makes it hard to assess their relative performance. We also need to remember that just because machine learning approach worked well on one design doesn't mean it will generalize to a design that we want to apply it to as part of our work or our verification process. Having some transparency to understand the complexity of that design is very important. In the research, however, some researchers don't state the design, perhaps for IP reasons. The most commonly we're told functionally what a design does, but not actually how it does it. Perhaps the best examples are where they use an open source design, which allows us to directly compare the design it was evaluated on to a design that we might want to apply it to. And that brings us to the last of our reasons of why we struggle to gain adoption. Well, in some ways, we've defined a very high level problem, improve the efficiency of choosing inputs to hit certain coverage points. As a result of that, researchers and engineers have created their own evaluation metrics and designs to tackle this problem on. And quite crucially, often don't make the code or the data available open source. As a result, that makes it complicated for someone wanting to work in this area to evaluate which technique is better, and also to then replicate the results. You have to pay a lot of upfront cost in creating a verification environment, setting up coverage models, before you can actually start any work. If you're from an industry background, I fully understand why, for IP reasons, you don't give away all your information. However, we also see some researchers benchmarking their results on open source designs, as well as ones that are in-house, and that can be a good compromise. And that kind of brings us to some of the opportunities that we identified in the research. The first one is there an opportunity for industry to drive the direction of future research through the use of open source data sets and verification environments. We've seen that work well in other machine learning areas, such as AI Gym for reinforcement learning or ImageNet for image classification. These reduce the barriers to entry, enabling more people to work on a problem and get up and running faster. So they're actually contributing to improving the state of the art rather than just creating the framework they need to get started. Popularity of open source designs, particularly RISC-V, for instance, is a good platform for that. There's also opportunities for researchers to provide better guidance on which technique to select. There's a trade-off between the amount of resources it takes to run a machine learning algorithm versus the amount of performance that you gain in terms of your verification process. That trade-off is rarely well understood in the research so far, and there's more work to be done there that would help us select techniques. There's also opportunities to look for synergies outside of hardware testing. So you've seen me quote a review into the use of machine learning for software testing. Many of their findings are analogous to our own. In particular, they also quote a lack of standardized evaluation criteria as a brake on progress. We also see within the software domain more experience perhaps with sequence generation. So for instance, when there's testing GUIs or graphical user interfaces. There are also applications more widely, so things like drone verification has similarities to hardware testing. You'll hear a little bit more about that later this afternoon. And if we take the problem in its widest sense, find inputs to drive a system to hit certain specific states, then you can look at things like agent-based AI for things like playing games or autonomous driving. So lots of things to look outwards as well. Now, this is very unscientific and approximate, but I kind of felt we needed something here to kind of summarize everything. So on the x-axis is roughly how hard or easy it is to set up and run one of these techniques. On the y-axis is approximately the level of automation. Based on everything you said, you should be very skeptical about the size of these boxes and where they're placed, because the information generally isn't known. However, as a general rule, techniques that are easy to supply are test selection techniques using predefined tests and binary classifiers. In general, things that are harder to use but have potentially more power in automation, reinforcement learning based for test generation, sequence generation, and done online in the actual main simulation environment. But I would stress, most of the information we need to make this doesn't really exist yet. That's something we need to create, the positions on the chart. Okay, thank you very much for listening. So you can find a copy of the review on arXiv. If you read it and find it helpful, please let us know. If you read it and don't find it helpful, let us know as well, so we can probably still improve it. There's been about 25 years of research in this area. It's not a new field necessarily. While classification helps us navigate that, it's still a complicated area. I think there's opportunities for industry to actually drive future research, but there's also opportunities for research to give better guidance on which techniques to select for any given context. And again, this problem is fairly broad. We can look for synergies with areas outside of hardware testing. Thank you very much for listening.
Yeah. There is one question on the line, Chris.
Okay.
And the question is about test bench, because you're doing the test generation. Is anyone trying to generate the test bench using AI ML?
Yeah, so we don't cover that in the review,
No.
but I have seen papers where people have used a large language model to effectively code a test bench from scratch. So literally saying, here's the design I want to verify, here's the kind of outputs I want to get from it, and it codes everything, the whole verification environment. So yes, there is research out there.
Do you know was it UVM or was it just directed or is it random? Or
I think it's a UVM, I think.
Okay.
Just manage expectations, it's very, very simple. So if you're into industry and you're using UVM-based test benches, this is kind of like the most beginner example you'll ever see, but nevertheless, it is possible to get machine learning to generate them.
Okay, thank you. I'm just aware of the time.
Yeah.
And then maybe time for one more. Okay, well, I guess the question is what's next? What's the next step in the research?
Yeah, so the background to this, we undertook this review because we are working in this area, that we want to do future research on it. I think for us, we have some experience of what we call novelty detection techniques. So these are effectively screening the tests as they're generated to say, is this novel? Is it different to what I applied before? It makes a potentially naive assumption that if you apply a different test, you'll get a different result in the coverage space or the states that your device is trying to hit and you're interested in verifying. But that naive assumption appears to work quite well. We need more work to know how well this generalizes to different devices. That's something we're going to be working on.
Okay, thank you very much. Thank you. Oh, sorry, there's one question from the audience.
Conspicuous lack of buzzword AI. Is AI just lumped in under machine learning, or is there anything we know as AI adds to this?
That's a very good question, and it kind of applies more generally. So machine learning is a part of AI. So it's not, AI would include lots of other things to do more with this, to like an intelligence view of the world. You'll see, particularly if you go to the research, you look for papers, the word AI and machine learning is sometimes used interchangeably. I'm being slightly more old school by saying it's machine learning because it doesn't worry about agents and kind of interaction with the world and that kind of thing that an AI research may look at. But there's a lot of similarities, and the techniques you might use in more general AI research would also be applicable here. Yeah, it's generative, and you in this field, because you are in principle generating tests, there is some research that looks at using transformer models, which is what the large language models are based on, to generate tests. But that's very early research at the moment.
Thank you. So last question, because then we have to move on.
So when I tried techniques like this in the past, the problem piece is being able to extract data like a coverage data, kind of dynamic, and reapply again to again dynamic. Did you have any techniques to overcome that?
That's a good question. Are you working in system Verilog at this point?
Yeah, I mean, because so system, it's been a while since I tried it, but that's the piece, the challenge that piece in the past was taking the coverage data, pushing it through some sort of learning and trying to reapply that as streams.
Yeah, absolutely. So there's typically, I think, so I showed on the slide, you tend to get an interface between your UVM test bench, which is written in something like System Verilog, and then all the machine learning side of things. I can forward you to papers that do that kind of work. So there are ways that people have found to do it. It's usually through some sort of interface. I think these tend to forward things through ports. I'm not a UVM expert. I don't build test benches, but there are ways in which you can extract that information, pass it into machine learning. Right? And there are papers that, their main contribution is we've found a way to do that. So there's work out there we can point you to.
Yeah, if you send the papers to me and Jason, we'll forward them on.
Yeah.
Okay, thank you very much. I'm gonna